going to go through FDP and drive perspective. We'll go through most of the major parameters there and just some drive perspectives on how we different trade-offs and how we as a drive will look at those parameters. For those of you that are not familiar with flexible data placement or FDP, here's a small overview. It compares well to streams and ZNS. I think mostly this is assumed background. I think that I don't need to go through this too much. The idea is that you could set up perhaps several applications and provide separated data so that it's stored separated and maintained separated is a possible solution there. From a terminology perspective, I will spend time going over how it's organized, so that way we have the terminology covered here. FDP is consisting of a drive with many reclaim units, and those reclaim units might be assembled in one or more reclaim groups. And you can use reclaim handles in order to point into those reclaim groups. So basically the reclaim unit handle, the RUH, is a pointer, and with the reclaim group and RUH, you're able to have find which reclaim unit you're currently filling and writing data into. A drive might support one or more FDP configurations, and the host can enable those on an endurance group. And when you provide those write commands, you can address and have data come in from a reclaim unit handle and the reclaim group and get exactly into the particular, the diagrammed red reclaim unit there. And there are, when you provide modifications, you can go through the RUH to provide those, some host management of those capabilities. For this presentation, I found it useful to have a pretend drive. I made up these numbers. It doesn't represent any vendor, including Samsung. I know that there are errors. I did that on purpose, but it's close enough. It's good enough to create a good discussion. I also added in some useful performance numbers for some of the discussion as well. Again, close enough. It's not correct. In images, I use this little toy drive because it's hard to draw something that has 16 channels and 16 NAND die and so forth. So please use your imagination. I just use this little toy drawing, right? It's just for illustrations. And yeah, it has 4 NAND channels, 3 NAND die each for 12 die. And for the most part, I'm focused on enterprise myself, and I believe that FDP is generally an enterprise feature. So I make all these statements for enterprise SSDs, really. I'm not really trying to cover smaller. So nominal enterprise stuff that you're going to see is 8 channels, 16 channels, and 4 and 16 NAND die. These are ballpark reasonable things that you'll find out there, right? So, so that's enough of the background. Let's get into a little bit of the reclaim groups. How many should we have in an FDP SSD? When you, as a customer, are asking for a drive to provide different configurations, what is a good and useful request? One focus discussion is 1 RG for the entire SSD. I have it diagrammed here on our toy example, just outlining the entire storage NAND is inside of that RG. Generally, this is something that leverages existing NAND management from the SSD, so there's a whole lot of carryover. SSDs have to ship a conventional drive. Every vendor does, so that conventional drive gets to leverage all of that knowledge and experience and apply it for all of the NAND. We have a lot of optimizations available. For example, performance. We could route around if there happens to be some activity on one erase block or one NAND die. We can route around sometimes. So we have a lot of freedom to do that. We generally have, as vendors, different various optimizations we continue to take advantage of. That goes for performance, but we do the same thing for endurance. So we'll shift erase blocks around and use various erase blocks composing different RUs. So this is something that as vendors we have a lot of experience, and we have to do this every generation. Looking at the other extreme here, I put up 1 RG per die, which is sometimes discussed. Over here I have the drawing on our toy example, 12 different RGs, 1 for each NAND die. And for this, we as a SSD, we need to be more restricted and confined. So our tracking is more granular, our decisions must be more granular, and our over-provisioning must be managed within each RG, right? We don't have that possibility of rerouting around. If we're told to write data into one particular RG, it's got to hit that RG. Even if it happens to be busy at the moment, we're going to just wait until it's available, and then we route it in. From a host perspective, there's increased host burdens, right? Because we don't have that ability to manage as many decisions. There's a capacity question, right? FDP as a standard doesn't currently have any guardrails for the host. A host could hypothetically have all of the data that they want to write and route it into one RG. And yes, the standard allows when it's overflowing, we will route the data elsewhere and we'll put it on other locations, other die. But there's a understanding that you shouldn't be doing that, and it's rarely going to be an optimized decision if you continue to route too much data into the RG. So we won't, we'll log it, we'll tell you, and you'll be able to query and find in the logs that you routed too much data in there, but we have to continue to accept the data and route it in there, right? So that host needs to pay attention to the capacity. And I gave an example already where the performance of these RGs can interfere with each other. If you happen to have some activity going on, we don't have an option of routing around. And same thing for the endurance. So there is increased challenges on what happens with the warranty. A little bit of a question. I think the general expectation within the ecosystem isn't really well established on what the warranty is when a host continues to be poorly behaved. And when a NAND die is overflowing with data, those would be vendor-specific decisions on what to do with the overflowing data. So the other thing with 1 RG per die configuration, something that I think is missing in general discussions as well, is that you generally have this, there's going to be some activity on NAND die, and I'll go with an example of a program failure. They're pretty rare, but I think that it will happen sometimes that you have a program failure. And if you were to have a host try and make decisions for this, you're going to have a latency to discover that there's a program failure from the NAND channel, following the controller delays, the PCIe link, the processor routing through the internal processor of the host processor, CPU interrupt. Then you have to do your initialization, software processing to actually make the decision of what you want to do on this particular program failure event. And then it's got to go back down through the system. So we're talking about the processor routing again, the PCIe link, again through the controller, the NAND channel, and now we've actually done something. We made the decision. And so now we took 163 microseconds in this example to make a relevant decision. In contrast, when the drive has to make a decision in reaction to this example, we have our NAND channel, some amount of processing, usually hardware optimized because we're very specific task, and then we go back to the NAND channel to deal with it. So we're much faster and responsive when there is a surprise that pops up. And I think that that's something that's often forgotten. And yes, I'm giving some latency approximations that change with every generation of every product, and that goes for the host as well. But I think that it's important to understand the context of these two types of behaviors. The other reality is that I gave an example of a program failure, but that's a very rare event. So in a more common scenario, then there's a discussion of, okay, well, let's open loop feed forward and just make some expectations of processes are going to be done and the die will be available. I think that that's very possible, but I think that it's good to remind again that those latencies that you need to feed forward are going to be different per vendor, per generation, and these are analog operations. So even at beginning of life for one particular vendor, there is some variation of when operations actually complete. So you end up having to put around some pretty big buffer guardrails to make sure that your operations will occur as you prefer them from a host perspective. So all of this, I go around and I say, well, the other contrasting is you provide all the information to the drive, and you accept that there's a risk that maybe there's going to be a program suspend happen. If, most of the time you just throw it in there, let the drive happen. There may be no conflict, or worst case scenario, there's a program suspend, which is on a similar order of magnitude as just plain doing all that work yourself. So why expend any processor, host processor cycles on it at all? Let the drive handle it, since it must have that capability of managing the NAND anyways. So summarizing from an RG perspective, I'm obviously recommending one RG for the SSD. It does leverage that hardware optimization. The NAND management as well. I think that there are still, even though I'm not in favor of it, I think that there will probably be continued discussion for more RGs per drive. And so yes, when you have more RGs per drive, you can, as you increase the RGs, you can increase and improve the specificity of the physical data placement. It will do that. At the increased cost of performance endurance, and the NAND-specific knowledge is harder to carry over across the different vendors and generations. And I think that one other thing is that if you were to go to the most extreme numbers, an SSD is likely to have hardware limitations on the maximum number of RGs. So some of the highest number of RGs can't be tracked by the internal hardware. I'm sure that vendors, we have to make some kind of decision and say, all right, this is enough, and stop putting in additional resources. Moving on to reclaim units. What is the size of a reclaim unit that I would recommend, and how does the drive look at those reclaim unit sizes? For this, just so that I can avoid having to describe the RG size, I'm saying that there's one RG per SSD for the moment. Normally, the RG scales to the size of the RU in most discussions, but it doesn't have to. So I'll just state that the one RG per SSD for this moment. We do want the RUs to align to erase block boundaries. So there might be a desire for a host to come in and say, I want your RU size to be, and whatever number they pick, 128 kilobytes or whatever number they make up. And because we need to align to erase block boundaries, we, as a vendor, have to say no. We need it to align to erase block boundaries. So it's going to be something that's determined by that generation of NANDs, and we will have to report what the options are for a host to be able to do that. Some RU examples. One is what I call a super block size, where there's one erase block per plane from every die. And so I've drawn it here in these green on the NAND die. You'll see it here. And so this is very large. It's in the example drive that I put in the background area. It's 24 gigabytes, so it is very large. There are other options. For example, here what I'm calling a way stripe. So it is across one NAND die across every channel. And we could take this way stripe, and so one erase block from every plane, from every die that is equally distanced from the controller, right? So this is the first die that I have diagrammed here, but you would similarly have 3 more in the image if you were to continue with another RU size. So this cuts down the size. We're now down to 1.5 gigabytes. And you could also come up with down channel sizing here. I have that shown here, down channel. And again, I'm calculating the example 1.5 gigabytes is based on, not on this image here, but on the backgrounds. And so that was 16 channels and 16 die per channel. So it ends up being the same value for this particular example drive. We could also have a die stripe where we have one erase block per plane. Here, with this example, it's 96 megabytes. And you could also even have one erase block per, one erase block sized RU, so 48 megabytes here. Yes, there's other things that are available. For example, I put up wrapping could happen, so you could continue to have more erase blocks from one NAND die. Those are possible, and I think that they're not really worth going into. I don't think there's any major advantage, but acknowledging that they're a possibility. When we get into the performance of an RU, we look at the NAND implications. So what can an erase block do? We're going to program in order. We're going to have to fill that erase block. But FDP also requires that we take and fill all of the data for an RU before we move on to the next RU. So we end up being bottlenecked by the NAND's program speed for performances. So just diagramming it out, here's one erase block per RU example, and when we as a drive vendor are filling this RU, we're going to have to program in every single word line, and we're kind of gated by that speed of that program. So we end up being filling it up pretty slowly. But we move over to the die stripe example, we have two erase blocks, we can double our performance. And so because of these kind of examples here, you can understand that the RUH performance ends up being determined by the RU size. Yes, there are other variations, but I'm not going to cover those. When we get into it, we end up being high queued up situations. We end up being gated by our NANDs. When you run these calculations out through various different configurations I just diagrammed, our superblock has the highest performance, of course, because we can parallelize the data across all of our die, have them all programming, so we end up getting much better performance with a larger RU size. So we do have that cost of a bigger RU, but we have a better performance for it. The host has mitigating capabilities, right? So they could take different RUHs and RGs and make them more parallel. So you could increase the number of RUH that you as the hosts are managing. If you increase that concurrent programming, then you can extract the same performance out of the drive at the cost of managing more RUHs. I think it's also useful, since I'm giving a little bit of drive perspective. Yes, I'm kind of implying here that generally it's okay to, if you needed to understand the data layout, it's probably very likely laid out in a similar manner here as I had the red arrows coming in. But you shouldn't depend on that as a host, right? So yes, I'm acknowledging that it'll generally land in that position, but don't go and start depending on it, right? If you were to try and hypothetically do an erase of one erase block in the middle, there's a lot of in-drive and through the host connection system as well, race conditions. So data can get out of order. And when we have a superblock, for example, we as a drive very well could route around other activity that's happening in the die. So we might take data and go out of order on purpose. So don't depend on this while it's been implied. Another impact that we've seen for RU size ends up trickling up into the host. And I know there's many names for it. I call it a host extent. I think SS table, blob, object. There's many names for it. So I call it a host extent here, which I think nobody else uses probably. But there's this host managed object, the host extent, and the host might be trying to fill it and deallocate on this host extent side. And so when they're managing, and it's a different size than the drive, it can be a problem. And realistically, I think that they will always mismatch. There's vendor-to-vendor mismatch. I think generation to generation, we have RU size changes because we're dependent on the NAND's erase block size. And the host software ends up getting developed separate from the SSDs. So until we get to a point where the host software queries the RU size and then is specific for that drive, I don't think that they can match. And since within one enclosure, you're going to have one set of host software dealing with many drives, and you might have different vendors swapping in and out, I still think even if you queried, probably in an enterprise situation, it's not really likely to expect the host software to change their host extent in order to match the drive. So from that perspective, we've done, these are simulations, and we've found that when RU size and host extent size do not match, that it still is helpful because the host is still managing large chunks of data, the host extent size here. And so what I have shown here is the system write amplification. So it's the drive and the host write amplification total, right? Everybody claims it's multiplicative. And we were curious, does it multiply? Does it get worse? And the answer is no. When you route your data, it can be multi-threaded. RUH is coming into the drive. As long as the host is writing and filling their host extents and deallocating and trimming those host extents as a unit, we found that there's, as a system, better write amplification always. And that there's no exception to that. So I have out here is a ratio of host extent to RU size so that we can be vendor agnostic. And you can see that we're always an improvement, even in the most extreme cases there. The other thing that we can see is that, yes, when you have a very small RU size, as a system, you can get better write amplification. I think that this is, that's true, and it's important to realize that this is also assuming the worst case, right? So it's a random extent fill and deallocate, so I purposely chose that, but the reality is that hosts generally have temperature sorting, and so they aren't really worst case. So this is as bad as you'll ever get kind of thing, right? So even if you start managing and routing and grouping some host extents together and others different, then it should, again, improve even above that. From summarizing everything that I discussed, the larger RUs maximize the performance of a per RUH basis. They permit an SSD to route traffic around within the RU. Where does it get placed? What's busy right now as a possible optimization the drive can do. And even with a large RU, it does improve the system write amplification. With smaller RUs, you'll need more active RUHs in order to reach the same performance out of the drive. So if we're back to that RG routing question, right? If you were to try and route your traffic in and you're managing more of them, you need more decisions, more concurrent, all to take care of how to get the best behavior out of your drive. And it does provide the best system write amplification for those small RUs. From the final major parameter that I wanted to speak through is what is a recommendable number of RUHs, and should they be persistently isolated. For every RUH, generally, you can expect that each RUH is going to require some resources from the drive, right? So we're going to need the NAND append point, which consumes some amount of over-provisioning from the drive. And every single RUH has the risk of these open block timers that then need to be monitored to make sure that we're able to have enough data to fill those RUs in a timely manner. We'll also need some buffers for the in-flight data and capacitors for any potential power failure, right? We're talking enterprise, we have power fail protection in this realm. When you take those RUHs and now instead of initially isolated, you add on that they're persistently isolated, we're going to have some additional drive resources. There can be an increased number of garbage collection append points. And I like to describe this for a host person is that you've kind of forced a drive to have kind of a multi-threading garbage collection that's happening there. That's a reasonable analogy that we need to make ourselves multi-thread our garbage collection. So that also means that there's increased SSD processing, tracking to consume, which will consume OP. We need to, with persistently isolated, we need to garbage collect and keep the similar data grouped within the same RUH. And of course, it's going to increase the development and validation time as you have those parameters increase. A final thing that isn't always appreciated is that increasing RUH counts can additionally risk the contentions on the NAND. If you had two RUHs that are active, they may both be trying to program on the same location. So there is, for every RUH increase, there's a quality of service that could be impacted depending on the workload. From a, sorry, is it? Yeah, let me check that. Did it? It might be out of battery. Maybe I'll just use this. Is this still on?
Yeah, it's muted. Yeah, please use that.
Yeah, that's fine. I'm okay with this.
Okay.
All right. Garbage collection, where was it? Okay. Yeah. FDP does not define the over-provisioning, the sharing, or the garbage collection triggers. And I think that there's going to be variation within the industry, what's implemented and what's beneficial. The simplest is drawn here, and it's a shared over-provisioning pool, right? So if we had two different RUHs that are getting written, the blue and the red, the blue is writing sequential here, and you can see that it's very compact. It's deallocating, shown it by the white growing on that one. So it's kind of a circular FIFO. It's very nice and compact, perfect WAF. We love that tenet. The red is a randomly written RUH. You can see that because it's randomly written, it'll invalidate all over. So the written pool ends up looking very messy and having a lot of, it ends up consuming all of the over-provisioning that it's allowed. Another alternative, just to contrast with that example, is OP restricted implementation, right? So this OP restriction kind of says for each RUH, I want to have only a protected pool of over-provisioning in the drive. For this, the blue tenant that's very nice is not going to use its over-provisioning. It'll stay compact and there's unused stored area. The red is really eating into the OP that it has, but it can't get outside of that boundary and get over into the other over-provisioning. With these two, these two are, you would look at this and you'd say, why not always use a shared over-provisioning pool? But I think that there may be a use case where actually you want the protected over-provisioning. For example, I think that the protected restricted OP is good in a noisy neighbor concern area, right? If that blue is not actually well behaved, maybe it's semi-well behaved, it still deserves good performance in some scenarios. So protecting the over-provisioning pool can have advantages. With when we take this over and we look at persistently isolated RUHs and we add in the garbage collection and over-provisioning question at the same time, we do have advantages with persistent isolation. We can use persistent isolation to give right amplification estimates per RUH. So that is an advantage to be able to provide that. We can have logical and physical capacity tracking that's added. So we have some ability to have that extra information there. We're still looking at other OP and garbage collection trade-offs. I just put in 2. We're looking at other ones as well. And I think that we're interested in understanding customer workloads a lot more. So if this particular topic is interesting, we would love to model it, understand it, and try and make the best decision on what gets implemented in drive hardware. Perhaps this needs to vary per deployment. Maybe server versus storage gets a different answer here. So I don't think that we have an answer other than highlighting that this is a place that we as an industry will end up maturing and developing knowledge on this as we ship more flexible data placement drives. I think it's helpful also to point out, while we're discussing persistent isolation versus initially versus persistently isolated, I think that this is FMS slides here I've just captured from a teammate. Actually, the next presentation is going to go into a lot of this. So the major thing I want to just highlight here is these are 2 different tenants that are both writing to the drive, different workloads, given different RUHs, and they're able to use an initially isolated RUH and receive write amplification of 1. So there is a desire where people might instantly jump to a persistently isolated RUH requirement. And I think this is the major takeaway here is to summarize, don't be so quick to jump to persistent isolation. You can do very well with initial isolation. And other than that, I think I'll let that topic up to Roshan to discuss in the next presentation. Yes, but over idealizing the requirement for persistent isolation is definitely, I think, an industry risk. I think put in the plug, the data placement twig is meeting on Tuesdays, and I think there's some fair attendance from the vendors. I think that there would be good contributions if more host perspectives were added. And summarizing what I've recommended here, I gave strong recommendations for 1 RG per SSD. Otherwise, I was not giving as strong a recommendations. I think that it is good configurations to have large RU sizes. I do see advantages for smaller RUs. And the RUHs, it's when you generally are speccing out as a customer, be careful against inflating your RUH counts. They do have impacts, and you'll see those and note those when you try and work with the drive. So moderate those RUH counts to be what you really want to deploy. And initially isolated RUHs can be very positive. I think, yeah, and I discussed the over-provisioning management and garbage collection triggers will be an area we will evolve. And with that, I can take any questions. Thanks. Yeah.
So the data placement technical working, will it produce like a recommendation or document? Is that the idea?
Yeah, so they're working towards a paper and thank you. The question is, does the data placement twig, what is the product that they're working towards? And they're working towards 1 paper summarizing a lot of this information of trade-offs and providing some recommendations. Yeah, so they're working towards that, right? So maybe you didn't like my opinion here. That's a good place to discuss it and make sure that hopefully that paper provides some industry alignment, right? So there's a little bit more commonality on if I'm writing software as a person and I don't know which FDP drive might be plugged in, there will hopefully be a common FDP configuration that you can boot up, look for, and start using, and it gives a little bit of focus for that software development as a hopeful product there. Yes, let's start here in the front, and I'll go to the back in a second.
So I want to hear your thoughts about the trade-off between the large RU and the small RU. So for example, when the RU is large, the host tends to do garbage collection themselves. But that means the host needs to read the loss of data out of the SSD, transfer to the host, and then write it back, which is more expensive than SSD doing it within the drive.
Okay, the question is, actually, let me go to the question image so that we can point to it. The question here is the host extent is a very large host extent maybe. So if you have a large RU and you have a large host extent, the challenge from host side is they need to read that out, garbage collected, and write it back into the drive. That's the concern. So I think that garbage collection traffic is true no matter what. There's a host side garbage collection that needs to move the data. And yes, I understand that when you hit your host side trigger to do garbage collection, you're going to need a garbage collect over a larger amount of data when your host extent is bigger. I think that the volume of GC ends up being the same on the host side, independent of the host extent size, right? You still, as a host, you're just managing this host extent versus a smaller host extent, right? I think the data movement as a whole ends up being the same. So I'm not sure that's a critical difference. I'm not sure.
Smaller host extent should have less GC cost because some host extents will become empty naturally.
So the question is, for smaller host extents, there will be less GC needed. And that's true, that is showing up here where we're showing that as, well, this is proportional, so I guess it doesn't really show up. But you're correct. When you have smaller host extents, they end up naturally being empty, so you don't have to do the GC. So I guess I don't have a well thought through response. I think that's a good thing I need to think more on. Thanks. There's a question. Yes. Yeah. Yeah, we are, so this particular one is a work, thanks, summarizing when we have mixed tenants that are not connected to each other and unrelated, does that break our conclusions, is a summarized question there. And I think that this image right here was a worst case scenario, right? So it's every tenant is as bad as could possibly be. And that's this one, right? So that's our results here. And then the other thing is that we are doing, this here is showing that we're real drives, we're seeing real performance to various tenants that are separated, running their own workloads, and they're disconnected from each other entirely, and it does drive towards write amplification of one. So I think, of course, we haven't run every single possible workload, but we are not seeing that any gap in our conclusions yet. We haven't found any gotchas from various tenants having different workloads. Not yet, anyways. I think you're right. We'll continue to monitor it, but it seems like we have robust conclusions so far. Yes, yeah. So the question is, are there any missing controls that we should add to FDP, or is it pretty complete feature set as it exists? I think that we're at a good point for FDP. It's one of those where I think there will be more, you don't want to over standardize, and I think that there will be a lot of evolution. So for example, we may be need to talk about the over-provisioning and garbage collection as something that can be controlled by the host. I'm not sure that that's true. I think there's advantages to letting the drives be able to make decisions. I think it leaves room for an evolving garbage collection trigger and OP management, those kind of inventions, right? So let the drives and the market end up having more maturity. So I think it's a good starting point myself. I have heard that there's some host people have said they would like a way to control the garbage collection occurrence a little bit more. I think that that's generally a drive allows, we want to be, it's a greedy implementation in most drives. So we allow our over provisioning to be filled and we trigger our garbage collection as late as possible. So we can't put it off anymore kind of a thing, right? So do you want to tell us to do GC early? That seems like an odd goal and I don't quite have my head wrapped around that one yet. So just focus on good deallocations is what I would recommend as a first step for those hosts. So, but I think we're at a good feature set for now. There's another question?
So, to expand on that question, if the design is solid, what's the point of having RGs at all? We should only have one per drive. It was designed there for a reason. What was the point? And why would we include it now? Why are you saying that it's not really worth using?
So the question is, if I'm recommending one RG per drive and that's the end recommendation, why do we have the ability and standards to have more than one RG per drive? And I think that, this is my opinion, right? And I think that while there's, I did acknowledge that there's advantages to the one RG per NAND die. And those advantages are real, and maybe the fear of the extra processing work is not so bad from one person's judgment. Maybe they say, I've got these expensive host CPUs and I got all the processing time in the world, I want to make use of them, right? So I think that, yeah, these are my recommendations and I would encourage these configurations, but I don't think everybody agrees with me. Yeah, so I predict that there will be other configurations out there just to serve different, other people that have different preferences.
To follow up on that question, so with YRG, would this be just another name of streams?
The question is, if you have one RG, is FDP essentially equivalent to streams? And I think that there's a ton of equivalences. I think that there is more reporting with the FDP logs. I think if you were looking at one RG configurations, you could have started with drives that do streams and added on a lot of monitoring features and gotten to FDP. So yes, I think there's a lot of similarities there. Yes, I think also those that have intuition on how to work with streams can carry that intuition into FDP, and I think it carries perfectly well. I actually think that's an advantage because people have that existing intuition about how to work with streams. The one thing that I saw in the streams ecosystem realm is that within the Linux community, I think it got not the best explanation. I think that there was some assumption that there was only data temperature separations, and sometimes maybe there's two VMs, they're both equally hot and they still want to be separated, and that's not a temperature separation. And so streams could have separated and worked for that use case, but it wasn't well described, and so it wasn't well understood in the community is what I have understood. So I think, yes, many similarities to streams, and yeah.
So streams, the scope of stream is within the namespace, but with FDP, the RU edge is across namespace. Do you think, what's the trade-off of these two decisions?
So the question is, streams has the streams within the context of a namespace, and FDP has RUHs, and then namespace is something that you can choose. So you could choose any namespace to write into one particular RUH. I think it's a matter of how you route things. I don't think it's a kind of an indifferent thing from a drive perspective. It's which way do you want to communicate things. I don't think it's critical there. Is there? Yeah. Yes.
Okay, one more response. The name flexible data placement is extremely carefully picked, and my favorite letter is F as in flexible. And yeah, you can run like a streams implementation. In fact, there's an almost no-touch version of the stream implementation, which is just assign a default namespace, and then the application doesn't even have to tag rights. But FDP, unlike streams, if you want to, maybe even call it host offload. If the host wants to offload some of the placement and garbage collection, it can say, I want a fresh RUH now because I want it separated from the other. I'm sorry, I want a fresh RU from the other RU, and then I can also at the end say I'm done with that RU, be allocated, and so the host can take on garbage collection or registration if it's so inclined. And you couldn't do that with streams. So there's this. The best part of flexible data placement is it gives you the ultimate control, or you can have the most simplistic of solutions. And it's up to you where your return on investment as a host developer is. If the simple solution gives you a fabulous right amp uplift than what you had before, you're done. If you want to keep going, there are optimizations you can take on and the simpler you can improve.
Yeah, that was a good answer. Let me try and repeat it for the recording. I will fail, but Steven's giving good. So flexible data placement has more flexibility, but it also has the extra parameters, and gave a really good example that you could, as a host, use the RUH the handle can be used in order to request a new fresh RU so that you can start off empty. And similarly, when you, as a host, are done writing, you could finish that RU and request another new one. So you actually have the ability as a host to have extremely fine-grained control over the drive's data placement, or optionally you can ignore a lot of it. And hopefully that's a sufficient good summary for
Can
the...
you start a new stream and put the write? If you write a new stream, that'll be a new RU, right?
So there's a question. The question is, if we start writing to a new stream, which is a new RUH, will it be a new RU? And if you, the answer is actually not as clean as you would think. If you plug your drive in and you start, then the answer is yes. But based on whatever else happened in the life of that drive, you can't assume that, right? If you have just booted up and you are working with a brand new drive you've never touched before, there is a possibility that that RUH was written to and that it's halfway through. So if it's high desirability to make sure that you are at the beginning of an RU, if you have that desire, then use the command to request that, I forget the terminology for it, but request a new RU, and that'll guarantee it. So use the correct commands, but don't just assume it. Just go ahead and set it as you desire it.
So RUHs are persistent to their associated RU across power fail and everything else?
The question is, are RUHs persistent across power fail? So the RU that they're writing, are they still writing that RU after a power fail? And I think I'm trying to make sure, I am not sure that there is a answer for all vendors. I think that there will be variation. I think that that would be a great place that maybe the data placement twig can address that. I know that we have a Samsung answer, and I think that in enterprise, because we have the power fail, I'm guessing that through the ecosystem, enterprise probably prefers the same RU across cycles. I think that the drives have the possibility of operating either way. So I don't have an exact answer right now on all the drives' behavior, though. That was good questions. Well, thank you. Those were really great questions. I appreciate it.